So here we have part 2 of the ideal gas. A formula that's used for ideal gases is PV equals nRT. We spoke about this a little bit before, where P is the pressure in atmospheres, V is the volume in liters, T is the temperature in Kelvin, and N is the number of moles. So again, these are for gases. We can use this equation. And R is a gas constant, which is 0.0821 liters atmospheres divided by mole Kelvin. There's also different constants if you look online, which have different units as well. So to use this equation, let's take a look at an example. A sample of chlorine gas has a volume of 8.56 liters, so this is our volume. The temperature is 0 degrees Celsius. We need to convert that to Kelvin, so plus 273. And the pressure is 1.5 atm. So let's just calculate the moles. We need to isolate, so we take our equation, PV equals nRT, and isolate the moles to get PV divided by RT. So we get N is equal to, we plug in the numbers, the pressure times the volume divided by the gas constant and the temperature, and then we get 0.57 moles of Cl2. And the units should cancel. The atmosphere should cancel with the atmospheres. The Kelvin, K to the minus 1, you can flip it over, which will cancel with the K, and the liters will cancel, and you're left with the moles in the denominator, and you bring it up, it becomes 0.57 moles of Cl2. So once you guys give this a try, you can pause the video. If we read the question, determine what each variable gives. So V, the volume, is 20 liters. N is the number of moles, 2.86. T is the temperature, so 23 degrees Celsius plus 273 is 296. And we plug in all those values for pressure, because they're asking for what is the pressure. So using PV equals nRT, we isolate the P, you get nRT divided by V. So when we put in all these values, we get 3.47 atm. So let's expand the idea. We use ideal gas again, but here we use, we're trying to find the moles. We also use the molar mass as well. So you'll see if you have 108 milliliters of butane, so we convert that to liters, which we did here for our volume. We have our pressure of C4H10, 715 millimeters of mercury. We convert that to atmospheres, so we divide by 760 millimeters of mercury, and we get 0.94 atm. And 25 degrees Celsius, as you guys know from now, you have to add 273 to get 298 Kelvin. So we isolate the variable we want is N. So we have N equals 0.94 times 0.108 divided by the gas constant divided by the temperature, 298, and we get 0.00415 moles. Well, that's not what the question, it's not the N, because the question is asking what is the mass in grams of butane. The butane is C4H10. So we have the moles. If you remember, if you have the moles and you want to convert it to mass, you need to find the molar mass of C4H10. So we have the moles in the previous slide. We want to find the mass, the molar mass of C4H10. So what do we need? We need our periodic table. So from the carbon, 4 times 12 is 48, plus 10 times 1, we get a molar mass of 58.1. So when we multiply that out, we get 0.241 grams of C4H10. Again, this is our roadmap. We have the moles. We want to find the mass, so we multiply by the molar mass. try another problem. Again, it's good to get familiar with this by trying problems. So how many liters of NH3 ammonia can be produced from 0.93 atmosphere pressure and 24 degrees Celsius? Of course, convert that to Kelvin from a 16 gram sample of nitrogen gas. So, and in excess of hydrogen gas. We say excess, we assume that the nitrogen gas is a limiting reagent. So here we have our pressure of NH3, we have our temperature of NH3, convert to Kelvin, we have the mass of nitrogen gas, so we'll have the mass here. We first need to convert to moles. Before we do that, we should check if we have a balanced chemical equation. We have 2 nitrogens on the left, 2 on the right, 6 hydrogens on the left, 6 on the right. So it is a balanced chemical equation. So let's go back to attacking this problem. We're given 16 grams of N2. So we divide by 28 because we want to find the moles of N2. Once we have the moles of N2, we use the ratio, a 2-to-1 ratio, to find the moles of NH3. So we multiply by 2, divided by 1 to give us 1.14 moles of NH3. So once we have the moles, we have the temperature, we have the pressure. As I just said, we have the moles. We can find the volume using the ideal gas equation. We plug in the values and we get 29.8 liters of ammonia. Let's see if we can use that same idea, a balanced chemical equation, to see if we can find the temperature of H2S. Remember, we can only apply the ideal gas equation, PV equals nRT, for gases. Okay, so that's another clue. So it says here 4 liters of H2S gas at 780 millimeters of mercury. So we have to convert this to atmospheres. So this comes out to 1.026 ATM. How did we do that? We did 780 divided by 760 millimeters of mercury. Gives us 3.5 grams of sulfur. So we start here on the right side with 3.5 grams of sulfur. So as step 1 says, we need to find the moles of sulfur. Use the balanced chemical equation to find the moles of H2S, and then use PV equals nRT. So 3.5 grams of sulfur. We have to divide by the molar mass. The molar mass of sulfur is 32 grams of sulfur for every mole of sulfur, and this comes out to 0.109 moles of sulfur. Once we have the moles of sulfur, we use the balanced chemical equation. So the ratio is 3 and 2. So what goes on the top, the 2 moles will go on top of H2S. On the bottom, 3 moles of sulfur. And here we get 0.0726 moles of H2S. Again, we cannot use moles of sulfur. We have to use moles of H2S because that's what the conditions that are given. And next we're asked to find the temperature. So we use PV equals nRT. T equals to PV divided by NR. We know the variables. We know P is right here, 1.026. We know the volume, 4 liters. We know the moles. We just found it here, the moles. And we know R, 0.0821. And we get 694 Kelvin. I think when we try, you get close to maybe 688, but that's close enough. 688, 690, 694 is fine for this problem. Another idea we can use is to find using density, because we know from chapter 1, density is mass over volume. So we can rewrite this formula. If you guys remember from our roadmap, if we have the moles and we want to find, or sorry, let's say we're given the mass and we want to find the moles, we divide by the molar mass using the periodic table to get moles. So we can use this idea of mass over molar mass, plug it in here, and then we have PV equals mass divided by molar mass times RT, and then we can isolate the mass and the volume, put it on one side to get M over V, which is density, and it comes out to this equation boxed in green. The density is equal to molar mass times pressure divided by RT. So using that equation, let's try to do a problem. It says find the density of carbon monoxide, units of grams per liter, at 0.9908 atmospheres at 55 degrees Celsius. So we have to convert the 55 degrees Celsius to Kelvin. So that we've done that, we added 273. We know the pressure. We know the molar mass of carbon monoxide, 28 grams per mole. We have to use the periodic table for that. And then we can plug in all those values to find the density, which we've done here. And we get 1.03 grams per liter. In terms of units, the ATMs will cancel, the moles will cancel, the temperature will cancel, and you're left with grams per liter. So I want to give you guys a try to use this. It's asking you to find the molecular mass, or molar mass of the gas given the parameters V, so the temperature of a gas in 30 liters. You can pause the video and try on your own first. V is in liters, so V is 30 liters. T, 21 degrees Celsius, converted to Kelvin, 294 Kelvin. So we added 273. The P is 0.5 ATM. And the mass is 12.6 grams. So with hints here, use PV equals nRT to isolate the moles. So if we do that, N equals PV over RT. So N is equal to 0.621 moles. So once we have the moles, we know the mass here. We can find the molar mass. So molar mass, I can just write molar mass is equal to mass over moles, and we find our molar mass, 12.6 divided by 0.621 equals to about 20.2 grams per mole. So that's our molar mass. The next topic is Dalton's Law, and hopefully this is a straightforward concept where they ask you the total pressure is equal to its parts. So P stands for pressure. The total pressure in this case we look at here, if we have gas A with a pressure of 10 atm, we have gas B with 5 atm, the total pressure A plus B is 15 atm. So this is the general formula for the total pressure, which is the sum of its parts. So let's try to apply that equation, where we have here a scuba tank contains a mixture of helium and oxygen gases where the total pressure is 7 atm. If the pressure of O2 gas is 1140 millimeters of mercury, so we have to convert that to atm. What is the partial pressure of helium gas in the tank? So we want all the pressures to be in atmospheres. So here's the equation. P total 7 atm. The pressure for oxygen is 1140 divided by 760, which comes up to about 1.5 atm. So we just have to isolate our helium. So we did this on the bottom. 7 minus 1.5 is 5.5 atmospheres for helium. We have here a new concept, which we'll derive in a second. We have here the total pressure, PA plus PB plus PC. We saw this in the previous slides. For each particular pressure, we can derive the ideal gas equation or implement that. So Na, the moles of gas A, times R, gas constant, times T, the temperature, divided by V. If we can do that for each partial pressure, we can come up with a equation where the P total, again, PA plus PB plus PC plus PD plus PE, etc. The common value for all these three terms is the RT over volume, RT over volume, RT over volume. So we can remove that from as a common factor and just have RT divided by V times Na plus Nb plus Nc. We also assume the gases don't react with each other and they're independent in the container. So now we can come up with a term for moles. So let's just take a look in more detail through an example. If gas A has a pressure of 2 atm and 3 moles, and make these respective conditions for gas B, gas C, and gas D in terms of atmospheres and moles, the total pressure is 15. And how did we do that? 2 plus 3 plus 4 plus 6 gives us a total pressure of 15 atm. We just showed in the previous slide how we can take out a common factor of RT over V. If I wanted to find the mole fraction, so this is a new idea, if I took the partial pressure of gas A and I divided it by the total pressure, we would come up with this expression. So remember, PA is Na times RT divided by V, and the total pressure is the sum of the moles, Na plus Nb plus Nc plus Nd, and you can have a common factor of RT over V, so those will cancel with each other. And you're left with Na, the moles of A, divided by the total amount of moles in the denominator. We call this the mole fraction. So this is a new term. Mole fraction is the particular moles of interest, for instance, Na divided by the total moles. And there are no units because they'll cancel. So we can do this for the partial pressure of A, we can do this for the partial pressure of B, C, etc. And it has a corresponding mole fraction, Na, which is divided by the total moles, to give us Xa. So then we can write an expression, a new expression. The partial pressure of A is equal to the mole fraction of A, Xa, times the total pressure. So box that in. And the general formula, Pi I can be A, B, C, D, E, etc., equals to the mole fraction of I times the total pressure. So here we have the equation, Pi, the partial pressure of the particular gas, A, B, C, or D, equals to the mole fraction, I, times the total pressure. It's good to keep in mind that the sum of the partial pressures must equal to the total pressures. So PA plus PB plus PC must equal to the PT. And the mole fractions XA plus XB plus XC, etc. must equal to 1. So let's try this problem here. A metal box contains 0.2 moles of oxygen and 0.4 moles of chlorine gas. If the balloon is at standard temperature and pressure, P total is 1 atm at, as you know, at standard temperature and pressure. What is the partial pressure of the oxygen? So we know the moles of oxygen and the moles of chlorine gas. So the N total is 0.2 plus 0.4 is equal to 0.6. If we want to find the partial pressure of oxygen, so we want to find the partial pressure of oxygen, it's the mole fraction of oxygen. So the mole fraction of oxygen, save oxygen here, is equal to 0.2 divided by 0.6, which is equal to 0.33. So this is our X, our mole fraction of oxygen. We plug this value in here. So this is 0.33. We know the total pressure is 1 atm. So 1 atm times 0.33 is 0.33 atm. So this is our partial pressure for our oxygen. Let's take it a bit more detailed. Give you guys a try. Here we have a gas mixture contains 3.44 moles of argon, 0.22 moles of xenon, and 3.33 moles of helium. What is the partial pressure of each gas if the total pressure is 2.44 atm? So let's first write the P total is 2.44 atm. Let's first find the mole fraction of each gas. So the mole fraction of argon is 3.44. Again, you can pause the video and try on your own first. I recommend doing that. This is from the question. Divided by the total moles, so 3.44 plus 0.22 plus 3.33, we get 0.492. Again, the units will cancel, moles and moles. Let's find the mole fraction of xenon. So here we have 0.22 divided by the total pressure, which again at the bottom comes out to, let's see if I can do this on my own, 3.44 plus 0.22 is 3.66. 3.66 plus 3.33 is 6.99. And this comes out to 0.0314. And we do the last one. Let's find the mole fraction of helium. Xe of helium equals to 3.33. Got that from the question, divided by 6.99. And this comes out to 0.476. So we have the mole fractions of each one. Now let's find the partial pressures of each gas is partial pressure of argon is the mole fraction. So mole fraction of argon 0.492 times the total pressure 2.44, and this comes out to 1.2 atm. So we should also check that our three partial pressures add up to 1. There might be some small fluctuation, but they should all add up to 1. Let me check. 0.49. Let me just check on my calculator. 0.492 plus 0.0314 plus 0.476. I got 0.99994, close enough. They should equal to 1. So let's continue with the problem. Let's look at the xenon. Of xenon, it's the same idea. You take the mole fraction of xenon, 0.0314 times 2.44 and this comes out to 0.0766 atm. And the last one, partial pressure of helium equals to 0.476 times the total, 2.44, and this comes out to 1.161 atm. So okay, the question was, what is the partial pressure of each gas? And here they are, and their respective values of 1.2 atm, 0.076 atm, and 1.16 atm. Last topic, the kinetic molecular theory of gases. So it assumes four things for the gases. You can draw a picture here. The gases, number one, gases are constantly moving in random motion. When particles collide with one another, or the walls, they bounce off each other. And they also, when they hit a wall, so if I put a detector here, let's say I put a detector here in green, when it hits the detector, it will exude a force, and that force can be translated in measuring the pressure. So when a gas hits the wall, it exerts a certain pressure which we can measure. So that will give us the pressure of the gas in this cube. The second one is the particles that make up the gases are so small that their volume can be ignored. So let's say this box is 20 liters. Technically, you would subtract that from the amount of particles inside. However, that is so small. The volume of those gases are so small that we assume that the volume of the box is still going to be 20 liters. Normally, you take 20 liters minus some small amount, which is comprised of the gases, that space that it takes up. But it's so small, we just assume that the volume stays at 20 liters. The gases, number three, the gases within the box, they don't interact with each other. They're not attracted or repelled from each other, so we consider them neutral. And the fourth one, this is kind of intuitive. If the average kinetic energy, so if the temperature of the gases increases, the particles will move faster as well due to higher temperature. So the higher temperature will resolve into a higher kinetic energy, and the particles will move faster. So the kinetic energy, Ke, is proportional to the temperature. The temperature goes up, so will the kinetic energy. The particles will move faster. As I just said, the temperature is related to their average kinetic energy. So we come up with this equation to calculate the speed of a molecule. I won't ask you to do any calculations, but just note that the speed of the particular molecules depends on the temperature, as we just said. And as well, this symbol here is the molar mass. So if the molar mass is in the denominator, if the molar mass goes up, this will result in a smaller speed. If we have a lower molar mass, the speed will go up. And that concludes our chapter 10.